Thank you. First of all, I would like to thank the organized committee and scientific committee for giving me this opportunity to participate in this conference. My gratitude to Professor Attila, President of this conference. It's a great pleasure to join you in this conference. I should introduce myself again. I am Professor Aladdin Kauka at Higher School of Teachers at Lagouat University from Algeria. I am head of lab Applied Science and Didactic. I am doing research about coatings and surface treatment of materials. Today I am talking about an interesting topic entitled Microstructure and Characterization of boride layers on titanium alloys and corrosion resistance. Following these outlines, first of all, we started by why we are interested about boriding treatment. Secondly, we will see the boriding process, and also why we are interested about titanium alloy, why we choose these materials for our study. And then we have some characterization of boride layers, microstructure and mechanical characterization. We have optical microscopy, scanning electron microscopy, micro-hardness as mechanical characterization, and fracture toughness of boride layers formed on substrate. After that, we have topological characterization and corrosion resistance of boride layers formed on substrate. And finally, we finish this study by conclusion and perspectives. So maybe you are asking the question why you are interested about boriding. Boriding, or is called also boronizing, as you know normally, it's a surface treatment, thermochemical surface treatment, which boron diffuse to the surface of treatment at high temperature, ranging between 800 to 1000 degrees Celsius for a few hours, between 2 to 8 hours. And due to good properties, improve mechanical characterization and mechanical properties of substrate. This substrate, it can be iron, cast iron or steel, and also in our case titanium alloy, and also we can apply it for cobalt and some super alloys. So due to beneficial and improve the mechanical characterization, boriding is a good choice for improve the certain tolerance application at, for example, trimming well, elixir for oil, boriding pipe fittings and gearings, and many others applications. It can be applied for boriding treatment. Boriding process, it can be applied solid, liquid, gas, on plasma, and ultra-fast boriding. For example, for solid, it can be applied with powder or paste. For liquid, with or without electrolysis. For gas also, or plasma, and PVD and CVD, physical vapor deposition and chemical vapor deposition. And now we speak about ultra-fast boriding. So we focus on solid because this is classic and very easy to achieve in industry. For liquid, the inconvenience that the samples that we will obtain is not clear. And for gas, usually we use toxic gas, so we avoid this process. And plasma-fast boriding is also interesting. However, it's more expensive than other process. So for our treatment, we choose solid boriding. So why we choose titanium alloy? In our previous study, we use iron, cast iron, steel, and many others iron-based alloy. So in this study, we focus on titanium. First of all, because titanium is promised materials, especially in biomedical, as biomaterials, and also for this process, we choose titanium alloy. It's relatively low density compared to iron at, for example, relatively low. It's between iron and aluminum. So this is why we choose titanium alloy, titanium 6 aluminum for vanadium. This is the most used in the industry, and this is the chemical composition of titanium alloy with vanadium, niobium, molybdenum, and other elements. And as I said before, titanium alloy, it can be applied on two big area in biomedical implant tooth, as you see here, and also in aeronautic and aerospatial. We focus our study only in implant tooth in biomedical. So titanium and its alloy have unique combination of high specific strength, as I said before, low density, relatively low density, and good corrosion resistance and excellent biocompatibility. So titanium alloy are favorite structural materials for a wide range of application in aeronautic, military, chemical, and biomedical industries. So this is the advantage of titanium. But however, unfortunately, titanium alloy has a limit mechanical characterization. So for their applicability in everyday application like the automobile industry, interest for materials interesting. So we try in this process to improve the mechanical characterization of our titanium by what? By boriding process. So this is schematic view of illustration boriding. As we see here, this is our sample in black color. This is our sample. This is a thermocouple with chromal type shield, and this is regulator, and here this is our crucible. We put it in the furnace, electric furnace. We are not obliged to use vacuum furnace. So at temperature ranging between 800 to 1000 for few hours, between 2 and 8 hours. In our study, we chose 950 degrees Celsius for 4 hours. This is the optimal parameters. This one is the optimal parameters. It's approved in our previous study. And the chemical composition that we have used, this is the chemical composition with silicon carbide, 90% of silicon carbide and 5% of boron carbide. This is called Ecabor, commercial Ecabor. You can buy it easily. So this is our samples. This is the samples that we get it after the treatment. This is our samples after boriding treatment. And then we try to characterize these samples with optical microscopy, scanning X-ray microscopy, and also mechanical characterization. We have optical, CM, and also X-ray diffraction analysis, EDS. And as mechanical characterization, we have the micro hardness and the fracture toughness of boride layers formed on the substrate. Sorry, this is the boride formed. This is the boride formed on the substrate. This is the substrate here, titanium substrate, and this is the layer formed. We see that's laminar structure, laminar shape, as you see here. This is the same. This is the structure. So as you know, the structure of titanium alloy usually it's equiaxed, and here it is laminar. So it's changed the form of boride formed on the surface of treatment. This is CM. And also with X-ray diffraction, we confirmed that we have titanium alloy, oxide titanium. Unfortunately, of course, we have oxide titanium and titanium boride and titanium diboride. We confirmed these phases by X-ray diffraction. So this is the structure before treatment, this one before treatment, and this one after the treatment. We see the diffusion of the elements. This is the titanium diboride. This is the titanium diboride. And this is the laminar structure here. You can see the formation. This is the boride layers formed, and this is the substrate, as you see here. This is transparent, and this the form of the microstructure. So in previous study for iron or carbon steel, before treatment and treatment samples, we have alpha iron, and after the treatment for borine, we have iron 2 boride and iron boride, as you see here, iron 2 boride, process in 3 baths. We use 3 baths: borax with boron carbide, borax with aluminum, and borax with silicon carbide. And we will see after that, we will see that with silicon carbide, we have only monophase. We have only iron boride. So with EDS analysis, we have the micrography for this. So we have in red color, this is the titanium, and this is in blue the boron that we have confirmed with EDS. For corrosion resistance, we found that the boride layers against corrosion improve and enhance the properties due to in aggressive environment, acidic, hydrochloric, sulfuric acid, nitric acid, due to the barrier formed of boride layers. The boride layers creates a barrier against the corrosion environment due to the compact and due to no reaction between the environment and the boride compound. So this is the boride layers, as you see here. This is the boride layers, and this is the surface exposed to attack by corrosive environment, and this is our substrate that we protected. So this is corrosion produced without treatment. In treatment, this is. So this is the optical observation of boron treated surface attacked by, in this case, sulfuric acid. So after 4 days, so we use here sulfuric acid, here as you see here, sulfuric acid and hydrochloric acid, and also sodium hydroxide and potassium hydroxide as alkanic solution, alkanic and based, also for strong acid. Unfortunately, we don't have good results against hydraulic acid. As you know, hydraulic acid is strong acid, so the results is less important than others. For example, sulfuric acid is with good results. So as we see here, we have formation of D boride. So here is iron boride, as you see here in this color black. This is iron boride, and this is iron 2 boride. This is iron 2 boride. And we have dental. It's not uniform. So we have a dental, and this is our substrate. This is our substrate. For borax with silicon carbide, as I said before, we have only monophase. Even that we increase temperature and increase the time, we have always monophase. And the thickness of boride layers, it can be attained until 384 micrometer, and this is very important, very interesting thickness. So we measure also the thickness of boride layers, and we studied the kinetics of boride layers formed, and we found that when we increase the temperature, there is increasing of thickness of boride layers formed on substrate. However, more or less increasing when we increase the time of boriding process. So we measure the thickness of boride layers. As you see here, this is the boride layers. This is boride layers formed, and this is zone transition. This one is zone transition, and the others is just the substrate, as you see here. Here is the same boride layers. This is boride layers, dental, tooth structure, and this is the zone transition, and this is the substrate. So after that, the same at when we increase temperature, and you see here, sorry, this is zone transition, this is the boride layers formed, and this is EDS. For iron, we confirmed that we have clearly the iron and little bit the carbon and less of bore. So we measure the thickness of boride layers with the classic and old method that we have in the literature. So with the average of 4 measure of boride layers, and we propose this is the thickness at, for example, this it's about 61 micrometer, and we propose another method using ImageLencher software. It's free software, you can download it in internet easily, it's free. So with this software we can measure the width, the height, and the string device and the area of all boride layers formed, and to calculate the substrate as you see here in different temperature and time. And also we use the profilometry surface. So for the left one, the left side here, and treatment without any treatment, and for the right side with the treatment. So we measure the profilometry. This is the longer, and this one to show the profilometry surface. After that, we try to measure the micro hardness of boride layers formed on substrate, and also the fracture toughness. So as you see here, this is the indentation. This is the indentation in iron boride in this layer, the first layer in iron boride, and this indentation in iron 2 boride, and this one in the substrate or zone transition. So when we go to the substrate, there is decreasing of micro hardness. This is the high. This point is the high hardness. As you see here in this table, the value of micro hardness for iron boride, it's about 2130, this one, until 2140, and for iron 2 boride is less hard than this one, and of course the substrate is not very high. This is the substrate of iron boride or titanium boride. And after that, we draw the curve of profiles of micro hardness as a function of depth of boride layers, and we have increasing of boriding. This is here in the surface. This is in the surface, and here in the substrate. So it's constant here, because we have increasing of boride layers. As you see here, this is the indentation of Vickers. This is indentation of Vickers as function of the depth, and we found our results. For fracture toughness, when we do indentation, we measure the crack. This is this one crack, or this crack. We measure the crack, the length L and C, to measure the fracture toughness of boride layers with this relation. So this schematic representation of different types of crack propagation, this is median crack and this is Palmquist crack. With this relation, we can measure easily the fracture toughness of boride layers that we have, the indentation load, the length, and the length of indenture. This is our results, and we compare our results of fracture toughness with the results that we have in the literature. This is our, in yellow color, this is our results, and the other color, this is in the literature. We compare our results. It's it's similar to the results that we have found it in the literature. And also we draw the boride layers versus boriding time at various temperature, 800 to 1000 degrees Celsius. We have linear with boride time. So we have linear curve, and also we try to measure the square of thickness of boride layers as function of time of treatment. And the thickness of boride layers it can calculate with this relation. We can calculate the diffusion also of boride layers, and the most important result to calculate the activation energy to create the boride layers on the substrate. So we have found, unfortunately, important energy activation. It's about 330 kilojoule mole. So after that, we try to measure the growth rate as a function of the inverse upside down of temperature, to measure also the activation energy, and we found relatively the same value. It's about 227 kilojoule for mole. So over mole. So we compare also our results. It's important energy in red color with that we have in the literature. So it's important, and this is the best one, I think, because we don't need activation energy. And also important results that we can predict the thickness of boride layers that we will obtain. With what? With our experimental results. We use with contour diagram, with the software, we draw the contour diagram of boride layers. So we have temperature as a function of time of treatment. So we can predict the thickness of boride layers that we can obtain. So for example, for this one, this is the line. So if I choose this point at, for example, here, this point, when I put the curses, this is if I choose at, for example, 870 degrees Celsius, and I choose for 7 hours, I will obtain how much? 130 micrometer. I will obtain it 130. If I do the experimental, I will find the same results. So this is most important, these results. And also, if we want a thickness, I want at, for example, a thickness about 150. So you can use for temperature, this temperature, at, for example, this temperature, 900, and for time 4 hours, you can obtain how much? 150 thickness. So we play on 3 factors: the layers, the thickness of boride layers, temperature, and time. So sorry, I don't have enough time, so I will be quickly to explain the tribological characterization and the structure, the scratch test. So due to the low chemical relatively big compound, and here as tribological, we found that the friction curve is low. We have low friction coefficient of friction is low. So this is important result. And also that means we have wear resistance. Abrasive wear or adhesive wear, we have good wear resistance for boride layers. As I said before, boride layers formed barrier and protection against corrosion and against friction to protect the substrate. So finally, we can conclude that titanium alloy was successful borided, and we use a new technique to evaluate the boride layers thickness, and we study the microstructure and micro hardness, also the fracture toughness of some characterization were investigated successfully. And the following results also that the microstructure adds changed for titanium alloy. The effect such changes for their mechanical improve the mechanical characterization and tribological, especially the wear resistance in abrasive and adhesive. And also for the corrosion, we found that the thickness of titanium alloy for alkalic or acidic sodium hydroxide, potassium hydroxide, and also for acidic hydrochloric and sulfuric acid, especially for sulfuric acid, good corrosion resistance for this process. In future work, we can apply the boriding process for other materials as cobalt, as superalloy also, and we can determine the activation energy of other bond substrate and develop the thickness model to study the growth boride layers considering the effects of these elements. So also other metals such niobium and tungsten in the future work. That's all. Thank you for your attention, and is there any question I am available to answer. تشكرا.